Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Flow Through Beds of Solids. Why should we need to study about flow through beds of solid particles when we have already studied flow through single particle or single particle settling in gravity and centrifugal field? Both the forces, both centrifugal and gravity fields we have seen. We have also seen hinder settling. So then what is the point of studying such kind of flow where the fluid is flowing through beds of solid particles? Why? Because flow through beds of stationary granular solids is often found in chemical and processing industries in a large number of applications. Let us say we have a kind of column in general like this, and then at the bottom of the column there is a kind of a perforated plate. So this plate is having some kind of perforation, right? So now these particles, whatever the particles that we are using them as a kind of a packing, they are placed on this perforated plate, so that particle sizes should be more than the opening of the perforation or perforation plate opening. Whatever these openings are there, so that should be smaller, and then particle size should be larger, so that they should not fall down, right? So then the particles are arranged like this. So sometimes this top of this bed is also closed with a kind of perforation plate, right? So sometimes it does not, it not necessary like there is a kind of a closing at the top. So when the fluid is allowed to flow through bottom like this, if this bed is packed or closed from the top, then these particles will not move. They will be a kind of stationary granular solids, like bed of stationary granular solids, right? Okay. So that means fluid flow is only taking place, or the only one phase, single phase flow, that is liquid phase flow, is taking place. If it is not closed at top, sometimes what happens, kind of particles will raise, will come to the some kind of fluidizing conditions, and then they will raise, and then the motion take place both the phases, like solid and then liquid phases, both phases will start flowing, or solids are floated in a kind of floated conditions, and liquids are flowing at a kind of certain high velocities, right? So these kind of situations are usually known as the fluidized bed, that will be discussing in after couple of lectures. So let us restrict our discussions in this lecture only to the case where we have a kind of packed beds, like, so that is the top of these beds are also closed with a kind of perforation plate, something like this. So these fluids are flowing through bottom, and then passing through this perforated plate, and then passing through this particle packing structure, and then going out of the bed, right? So in general what we have, if you have a kind of single column like this, the fluid just flows through, and then fluid elements will travel the distance equal to the length of the pipe or the column, whatever we have taken, right? But here now part of the column is packed, or mostly most of the sometimes entire column is also packed, so let us take only this part only packed. So then what happens, let us say the full fluid element coming here, that may go from here like this, take this path, and then go from this corner like this, or the same fluid element will take this path and then go like this, and then come out like this, or this one may go like this, and then like this, and then go this path like this, whatever that I have drawn. So that means it may take any path depending on the resistance offered by the neighboring particle, and depending on the size and shape of the neighboring particles and all that. Okay. So that means the packing length, let us say if the packing length is L, so it is possible that particles are traveling more than this L distance, because of this tortuous path. Okay. So that is one thing. So now coming to the applications, why should we need kind of this kind of flow through packed bed should be studied? There are several applications, right? So here what we are going to do, we are going to measure a kind of expression for pressure drop as a function of packing characteristics like porosity, tortuosity, etc., and then particle size that has been used for the packing, shape of the particle, then the density, viscosity of the fluid, etc. in terms of measurable parameters, including this L also, the height of the packing. So, in terms of measurable parameters, we are going to develop an expression for the pressure drop. Similar way, like for a pipe flow, if it is a kind of laminar flow, delta P by L is equals to 32 mu V by D square, or delta P is equals to 32 mu V L by D square. This is what we have already seen for Huygens-Poiseuille equation. So, corresponding equation here, what should it be? Because here in the case of packing, there is no kind of abstraction. So, they are simply flowing through, but here there are large number of particles are there. Each particle may be offering some kind of resistance to the motion of the fluid. So, the overall resistance offered by all the particle, that should be the overall resistance experienced by the fluid particle to pass through the this kind of channel. So, this is what we are going to see basically, right. Then coming to the applications in general, what happens? So, catalytic bed reactor, let us say in H2SO4 plant, what happens? So, there is a SO2. So, in general SO2 is in H2SO for plant, SO2 is there, that will be passing through a kind of a catalytic bed. So, catalytic bed. So, that is catalytic bed or catalytic reactor. So, then here, so whatever the SO2 comes out, that will be reacting in the presence of this catalytic bed. So, that will be forming SO3, and then that will be further absorbed into water in order to produce the H2SO4 like that. That is one kind of example. So, another examples, drying of materials. Sometimes you have a kind of silica gel, etc., molecular sieves, etc., here in order to fulfill this drying aspects. And then also we have a kind of sometime this heat recovery system. So, let us say high temperature fluid is coming here. So, whatever the heat that high temperature fluid is carrying, that will be absorbed by this packing material here, and then the fluid will be going as a kind of low temperature or the ambient temperature fluid after passing through this bed, right. So, then whatever the heat is there, that will be heat storage kind of things. So, this heat storage may be sometimes when required, that can be recovered for the some other applications. Let us say then when you wanted to do the recovery of the heat, you can pass through a fluid which is having the low temperature, and then when it pass through, it may be carrying the energy from the this heat stored packing material, and then may be going out as a high temperature. That is also possible. So, both heat storage and then heat recovery, also these packed and fluidized beds are in general used. Then we have a kind of in general filtrations, like when we do the filtration, there is a kind of filter paper here in general like this at the bottom in a container, right. So, the slurry or the suspension comes out here, right, and then some kind of pressure delta P is applied, some pressure is applied, or there is a kind of vacuum at the bottom, either way it is possible, right. So, then when you take this slurry here, so the particles they may be settled at the bottom here like this, okay, and then clear liquid may be collected at the bottom. So, in these cases also, this is downflow, this can be treated as a kind of downflow packed bed. Whatever the examples I have shown here are kind of upflow packed bed kind of things. So, it is possible downflow, upflow, both of them are possible depending on the applications, okay. So, here this whatever the particles these present in the suspension, they are going to offer some kind of resistance once they settle on a kind of filter medium. So, this can also be taken as a kind of example where packed bed, flow through packed bed is taking place. Initially only the filter medium is resisting, providing the resistance to the flow. So, that is allowing only fluid element to pass through and then retaining the particles, so that the separation is taking place. But gradually as the process progressing, these particles may be settling on the surface of the this filter medium. So, they are also additionally adding resistance to the flow for the later coming in slurry, right. So, there will be two resistance, one resistance for due to the filter medium, another resistance due to the settled particles. Okay. So, in the next module we are going to discuss the filtration aspect. So, there we are going to see the equation that we are developing in this lecture are going to be useful in order to understand what is the resistance offered by these particles in designing of this filtration equipment. Okay. So, there are only a few reactions or few examples I have shown here. We have a kind of some examples. We have seen there is a kind of reaction taking place, there may be a kind of heat transfer, heat recovery, there may be sometimes some kind of mass transfer also taking place, right. So, all these three may be taking place or individually, or they may be taking place together along with the momentum transfer. So, whether the reaction is taking place or heat transfer is taking place, mass transfer is also taking place in addition to the momentum transfer. So, whatever the study that we are going to do here or analysis that we are going to do, that is going to be there in all of these things, right. So, that is whatever this reaction, heat and mass transfer are expected to carry out here in this packed bed, they will not be possible unless there is a kind of momentum transfer. So, there is a transfer of the momentum. So, how much pressure drop is required for a given flow rate of liquid to flow through a packed bed of having certain characteristics like voidage, particle size, packing particle size, dP, etc., those kind of things. So, this dP we are going to find out. Okay, right. So, this is the purpose that we need to understand flow through beds of solid particles, though we know the settling of individual particles or free settling and hindered settling of particles or suspension we have already seen. So, despite of that one, we need to understand flow through beds of solid particles because of giving so many examples here. Okay. So, what we understand, the pressure drop across the beds due to the resistance caused by presence of particles is a kind of prerequisite, because we have seen this example, several examples, the fluid is flowing through packed bed, and then when it is flowing through the bed, it is offering or it is receiving so much of resistance because of the particles that are used for the packing of the column, which is forming a kind of packed bed, right. So, this particle are offering a huge amount of resistance in general. So, that is going to be very much important. Let us say pressure drop, for the same pressure drop, if you allow a fluid to flow through a single column, you may be getting higher velocity, something like 1 meter per second, but under the same pressure, and if you do the column with some kind of packing of let us say voidage 0.4 or 0.5, and then you apply the same pressure, then whatever the velocity that you get, that will be much more lesser than the 1 meter per second of the individual column without any packing, right. So, that means the velocity, the average velocity in a kind of packing is also going to be very much different compared to the average velocity whatever we expect to have a kind of single column without any packing. Okay. So, that is the reason. So, pressure drop here is going to be very much important in designing of this equation. So, we have to find out proper way how to find out this pressure drop for a given system. Further, packing materials in general, they can be spheres, they can be irregular crushed particles, they can be cylindrical particles, small cylindrical particles, there may be small rashing rings, etc. They can be anything. Usually, spheres or cylinders or crushed glass particles, etc. are in general used the kind of packing material, right. So, in general, in reality, when this bed is forming, if the particles are of uniform size and shape, then there is a possibility that whatever the packing is there is forming a kind of uniform packing is taking place. But if you have a different size particle, though same shape, let us say you have a spherical particles, shape spherical, but different size particle 1 mm, 2 mm, and then let us say 5 mm particles if you use, the packing is not going to be uniform in general. And then further, if both size and shape are not same, if you have some spherical particles, some cylindrical particles as a packing, so it is not going to be uniform everywhere within the bed, right. Further, if you have a kind of irregular particles, crushed particles, something like that as a kind of packing, then the packing is going to be varying from one point to the other point. But theoretically, what we assume, and whatever the analysis that we are going to do, we assume that the packing is uniform everywhere and there is no or little channeling occurs. Channeling in the sense like the bed is there, let us say this is the bed. So, within this bed somewhere you have a kind of this kind of channels which is allowing the fluid element to flow through without any kind of hindrance kind of thing. So, particles are being segregated and forming a kind of channels kind of thing, right. So, because of this channeling the particles fluid element may be offering the fluid element may be receiving a little bit less resistance, but that is not going to be useful in many cases, especially if there is a kind of heat transfer or reaction is there. Okay. So, this channeling may be occurring in general in reality, but we assume that channeling is very less or almost there is no channeling. So, this is what we some basics what we are going to do about these things, okay, about the packed bed. So, then coming to the applications once again, fluids in general liquids or gases are passed through a bed of particles in several applications. For example, fixed bed catalytic reactors such as SO2 to SO3 converters, then drying columns containing silica gel or molecular sieves, then filtration of suspension, liquid flows at low velocity through these spaces between particles which have been retained by filter medium as explained. Then sometime deep bed filtration is also used on very large scales for water treatment, but however in such applications the particles that are being settled very few particles. Okay. Pressure drop of flow through a bed of small particles provides a method of measuring external surface area of powders such as cement or pigment. So, cement or some kind of pigments particles are very small, very small, measuring their surface area and then surface to volume ratio in general very difficult for a given sample, right. So, if you know the pressure drop, indeed we are going to obtain expression pressure drop for the laminar flow, pressure drop for the turbulent flow. So, under such conditions we have, let us say, if you know the average velocity experimentally, then you can know the Reynolds number. If you know the Reynolds number by experimentally, then you can know the pressure drop experimentally, right. You can experimentally also you can calculate the pressure drop. So, the corresponding to that pressure drop, what is the velocity etc., you can calculate, and then you can use the equation that we are going to apply here. So, then what we understand, we find out something like 6 by pi s dp, these kind of expressions are there in our equation. So, which is nothing but Sp by Vp. So, this Sp by Vp, finding Sp by Vp is very difficult, especially for very small particles in general. That has to be generally done by microscopics, but you cannot use microscopic analysis for large number of particles. And then also microscopically, if you see, there are different dimensions, right, Farad dimensions and Stokes dimensions etc. we have seen. Let us say if the fine particle, if you see in the microscopy, if you taking having this kind of shape, let us say, right. So, which dimension should you take? Should you take this dimension? Should you take this dimension? Or should you take this cross sectional dimension? Which one should you take? This all we have seen like in one of the previous lecture of first module. So, because of these reasons finding out this Sp by Vp ratio in general very difficult for very fine and then irregular particles. So, for that what you can do, we can find that overall Sp by Vp from these pressure drop calculations. What we can do, we can take this particle in a kind of column as a kind of packing material like this, right, and then you allow some fluid to flow, non-reacting, non-corrosive fluid to flow through these particles which is forming the bed, and then for this bed for this velocity V naught bar you calculate what is the pressure drop experimentally, right. So, now theoretically we are going to develop delta P by L or minus delta P by L expression for packed bed, right. So, it is having some terms like 6 by pi s dp, something like that we are going to derive. So, that means if delta P by L you calculate experimentally, rest everything in the right hand side is in general known, like velocity of the fluid, voidage, and then density of the fluid, viscosity of the fluid, size of the particle used for the packing etc., those things are known. right. So, or size of the particle, if you assume that it is not known from theoretical point of view. So, then experimentally whatever delta p that you get, that you use, and then only in the right hand side you may not be knowing 6 by pi s dp. So, rest everything is known. So, then 6 by pi s dp you can calculate, which is nothing but sp by vp for a given irregular particles. So, this is how we can measure the surface, external surface area of powders of such small size irregular particles like cement and pigment by using this flow through packed bed experiments. So, that is also possible. Indeed, this as we have seen as a one kind of application in one of the earlier lectures. Okay. So, this 6 by pi s dp is equals to sp by vp. From where are we getting? We are getting from the definition of pi s. Pi s is 6 by dp divided by sp by vp. So, 6 by dp is nothing but surface to volume ratio for a spherical particle of equivalent diameter. Sp is the surface area of the regular particle, vp is the volume of the irregular particle. So, from that definition it is coming. This also we have seen, and then we have done several problems also on these things, right. So, now what we understand, the resistance to the flow of fluid through the voids in a bed of solids is resultant of the total drag of all particles in the bed, or the total resistance offered by all the particles. So, that is going to be the overall resistance to the flow of fluid. So, but as in the drag of single particle, there is a sharp transition between laminar and turbulent flow in general in our single particle cases. We have seen, like if the Reynolds number is less than 0.1 or less than 1, we say that it is a kind of Stokes regime, or if it is a kind of a case flow through pipes, then we know that REP or the RE for a kind of pipe flow case, if it is less than 2100, we can say that it is a kind of laminar flow. If it is more than 2100, we can say it is a kind of turbulent flow. Such kind of sharp transitions in general are not possible in the case of flow through packed beds. In general, indeed, we know that from experimentally it has been found that the flow through beds of particles is laminar only for small ranges, let us say up to REP 5 to 10 only. If it is more than 10, it is not going to be under laminar flow conditions anyway, right. So, such kind of sharp transitions are not possible in the case of packed bed. Thus, most common method of calculating the pressure drop through a bed of solids are based on the estimates of drag on solid boundaries of the tortuous channels through the bed. So, actual channels in general are irregular in shape. Okay. We have a variable cross section and orientation, and are highly interconnected porous structure in packed bed in general, like this. So, these particles are in general not necessarily spherical, they can be kind of needle like, they can be crushed particles, irregular shaped particles, they can be like anything, right. So, because of that one, actual channels in general they are irregular shape. So, this flow channel, flow channel in the sense whatever the free area, free volume area that is available between the particles, right. So, that is very irregular, okay. And then we have a variable cross section. If it is a flow through a column, so then the cross section is a constant from the inlet to the outlet of the column through which the fluid is flowing. But if that column is packed with some kind of packing material, so then what we have a kind of cross section is varying. So, here the cross section is different, here the cross section is different, here the cross section is different from one location to other location. Cross section in the sense cross section of the flow channel which is available for the fluid to flow, and these channels are also highly interconnected in general. Okay. So, however, we have to calculate the pressure drop. So, how to calculate pressure drop? Calculate an equivalent channel diameter. It is assumed that the bed has a set of uniform circular channels whose total surface area and void fraction match those of the bed. Okay. So, now actually this why are we doing this flow through packed beds in general? Though we have seen there are a kind of catalytic reactions, there is a kind of heat recovery kind of system, there is a kind of mass transfer in something like drying, etc. So, then what is the point? Why are we using these things in a kind of packed bed? Why not we doing in a kind of single column or individual columns like that? That is because when we have this packing, the surface to volume ratio for a given packing dimension, it increases. It is very much higher compared to the single columns. So, that is the more surface area you have for this transport process to occur, or the mixing kind of operations to occur, or whatever the momentum, heat or mass transfer or reaction is taking place, that its degree of performance would be higher because of this higher surface area provided because of this packing. That is the reason we are doing. Okay. So, now what we understand, this total surface area is the one very important one, and then because of this thing, this packing, etc., what we have within the voidage within the column, we have a kind of void fraction. So, these two are going to have a kind of important role along with the particle diameter, along with the density, viscosity of the fluid, and then height of the packing in measuring this delta P. Okay. So, these are the kind of things are playing role here if you want to find out this dP. So, but theoretically it is very much difficult, like the flow is very irregular and indeed very complex from one channel to the other flow channel, or from one location to the other location within the packed bed because of the irregular channels, variable cross section, orientation, and then highly interconnected channels, etc., present in the packed beds, right. So, then how to do this one? So, now what we do, we assume this bed whatever is there, simplify rather than assuming, simplifying, this is the bed packing, let us assume. I am just making a kind of circles kind of thing. So, do not take it granted for a kind of only spherical particles. The analysis that we are going to do, that is going to be valid for all the particles, all types of all shapes, irregular, regular, irregular, small, big particles, all of them it is valid actually. Okay. So, now what we do, we have to equally represent this packed bed in a kind of workable geometries kind of things. Here what we have this epsilon, and then this channel dimension, that is varying variable cross section, etc., right. So, that these things are there, right. So, we have to worry about the void fraction of that is free space available for the fluid to flow. What is the free space available? That is the interstitial spaces between the particles, that we have one parameter, and then the surface area, the other one we have to worry about, because these two are the additional thing compared to a kind of a single column. If you have taken a kind of single column, this is packed bed, now single column or flow through pipe kind of things. So, if you take these two cases here, now what is the difference? Only this packing is there, and because of the packing, this epsilon and then SP by Vp are the kind of things which are making a difference, newly being added up. So, what we do, this system we have kind of we will try to generalize or simplify, so that we can easily do a kind of analysis and develop a kind of expression as we develop for this case, like delta P by L is equals to 32 mu V by d square, like this is Hagen-Poiseuille's equation, that for a laminar flow through pipe, the pressure drop is this one can derive this one in fluid mechanics course, right. So, this is the one we have like for now this column, when we are adding some packed material or material for packing, then these two things are additionally coming. So, this system we are generalizing it. How we are generalizing now, or simplifying like this? We are taking a few number of capillaries Okay, right. We have these capillaries like this, through which the flow is taking place like this. Okay. The diameter of this capillaries we take, let us say d capillary. The height of the capillaries is same as the height of the packing here. Okay. So, now these n number of capillaries, so what we are saying, they are n number of capillaries. So, these capillaries, what we are saying, we are bunching together, we are adding together, like we are forming, like we take n number, let us say this is one capillary, like n number of capillaries are there, we are making a kind of bunch kind of thing. So, bunch of capillaries. Okay. So, how many capillaries we do not know, let us say n. So, what we are assuming that these capillaries, when you are taking n number of capillaries, whatever the white space is provided, that is the area internal volume of the capillary through which fluid is taking place, right. For all the capillaries, if you add together and then find out the fraction, so then that space, the void space available for this n number of capillaries is same as the void space here in the packed bed. That is how we are going to do. So, we are replacing, we are getting n number of capillaries having same height as the packed bed height, right. So, those n number of capillaries are forming a kind of a bunch of capillaries and then allowing the fluid to flow through, right. So, then the whatever the void space that is available in this bunch of capillaries, that is equal to the void space of packed bed, that epsilon that we have taken, such that n number should be decided, right. Should it be 10, 100, 1000, that we do not know, indeed we do not want to know at all. So, but theoretically this is what the one representation that we are doing, that is one. And then next one is the surface to volume ratio. Whatever the surface to volume ratio here in this n number of capillaries are there, that is same as the surface to volume ratio for the packed bed. Okay. So, the n number should be decided such that for the bunch of capillaries, whatever the epsilon and Sp by Vp are there, so they are same in the case of packed bed, or they should be equally equivalent to the whatever we have the packed bed case. Okay. So, this n one has to find out. In reality we may be thinking, but we do not need to find out, let us assume this is n. Okay. So, this we are doing. Now, here this representation, this d equivalent is there, the diameter of the capillary is d equivalent, that is the flow channel dimension, okay, or the dimension which is providing the space that is through which the fluid is flowing in the capillary. Now, this d equivalent we are going to find out as function of this epsilon, packing particle diameter, etc., for a given real system. That is what we are going to do. Okay. And then here whatever the d in Hagen-Poiseuille's equation is, d is there, there we replace d by d equivalent, and then v we replace by the superficial velocity v bar. So, v bar is a kind of a superficial velocity of the packed bed. Superficial velocity in the sense, like empty tower velocity, like this column is there, this is the same column here, this second one, right. This column, packed bed column is there, right. Whatever the dimensions are of this packed bed column, and then dimensions of the empty column are same. Then whatever the velocity is there through the empty column under this constant same pressure drop as in packed bed, that is known as the superficial velocity, or simply superficial velocity is a kind of empty tower velocity when there is no packing, right. But here this v should not be kind of v naught bar, because v naught bar is a kind of velocity that is passing through as a superficial velocity, but the true velocity here in the packed bed, the average velocity of the fluid element when it is passing through from inlet to the outlet, it may be having some average velocity, that average velocity V average should be taken here, right. But we understand this V average is nothing but V naught bar by epsilon here. So, those things we substitute here and then simplify this equation, so that we get the pressure drop equation for this n number of capillaries, which is same as pressure drop for this packed bed. Why it is same for this packed bed? Because this bunch of n number of capillary, whatever the characteristics are there, that is their epsilon and their SP by Vp, they are same as this packed beds. That is the reason they will be same, right. So since these capillaries also kind of circular tubes, something very fine small diameter tubes kind of thing. So here also Huygens-Poiseuille equations are valid. Indeed, for those capillaries only, this Huygens-Poiseuille equation is more reliable, because of laminar flow conditions can be established in capillaries much easily, right. So this is what we are going to do now for developing this expression for the pressure drop. So total surface area of the bed should be surface area per particle multiplied by total number of particles, that we should do. Then it is made convenient to base the calculation on the volume fraction of particles in the bed and the surface volume ratio for the particles. Why? Because if you take surface volume ratio particle, then you can also bring in the information of sphericity. If you bring in the information of sphericity in equations, that means you can also use those equations for irregular particles. Okay. So then for spheres, the surface to volume ratio, we know it as 6 by dp, that is nothing but surface area of this particle, that is pi dp square divided by the volume of the spherical particles, pi dp cube by 6. dp is the diameter of that particle, let us say. Okay. 6 by dp. So that is from where it is coming, 6 by dp, that is pi dp square, that is surface area of spherical particle divided by the pi dp cube by 6, that is the volume of the spherical particle. Then you get surface to volume ratio for spherical particle as 6 by dp. This is for the sphere, but we wanted to bring in the non-sphericity or irregular particle nature also into the consideration. So for other shapes or irregular particles, it should also include the sphericity, which is defined as surface to volume ratio of sphere divided by the surface to volume ratio of the particles, right. So then from here, that we have already seen that pi s is equals to Sp by Vp for sphere is nothing but 6 by dp, and then for the irregular particle surface to volume ratio we do not know. So let us keep them as Sp by Vp. That means Sp by Vp is equals to 6 by pi s dp. That means somehow from your calculations that you are going to do, or somehow from your results, if you can get the pi s by dp information for unknown irregular particles, then you can indirectly know the Sp by Vp ratio, or that 6 by pi s dp if you do, you will get Sp by Vp. That is not the primary object. For the time being, I am giving as a kind of information, because we have seen it as a kind of a application for finding out the surface to volume ratio of irregular material, irregular very fine materials. Then particle volume fraction in the bed is 1 minus epsilon, whereas the epsilon is porosity of void space, or the volume fraction of the empty space, or the volume fraction of the liquid within the bed. So whatever the empty space between the particle is there, only that much space liquid can occupy, that is porosity of the void fraction. Okay. If particles are porous, then pores are generally too small to permit any significant flow through these particles. Actually, when we are taking the particles, this analysis we are assuming the particles which are used for packing, irrespective of their size and shape, we are assuming they are non-porous. Okay. The analysis that we are doing, that is non-porous. But however, even if you have some kind of porous particle, their porous structure are too small in general to permit any significant flow through these internal pores also. The porosity whatever we are talking about, that is only for the external porosity only, or the interstitial space between the particle only, not for the porous structure of the internal porous structure of the particle. So we are assuming indirectly that the particles are non-porous. Even if they are porous, the flow that is going to take place through this internal porous is going to be much more smaller than the flow that is taking place through the interstitial spaces or external porous structure, right. So, that is the reason one can safely ignore the internal pore structure of the particles in these packed beds. So, thus epsilon is the external void fraction of the bed, but not the total porosity of the particles. Now, we find out equivalent diameter of the capillary channels, n number of capillary channels that we are taken. So, the diameter is D equivalent. This D equivalent we are going to find out as function of epsilon or the size of the packing material, etc. Okay. So, the actual bed is approximated as bunch of n number of capillary tubes packed together, and the flow is taking place through the capillaries. So, that is what we assumed as I explained before. So, the surface area of n parallel channels of length L should be the surface to volume ratio of particles multiplied by volume of the particle. So, in real packing conditions, whatever the surface to volume ratio is there, that if you multiply by the volume of the particle, so then that would be giving the total surface area of the packed structure or packed bed, right. That should be equal to the surface area of one channel of length L multiplied by the total number of such channels. Okay. So, that means if you have n number of channels or capillaries, okay, the surface area of each capillary is pi d equivalent L or pi d L for because they are cylindrical capillaries. Okay. So, the capillaries are each of them are having surface area pi d equivalent multiplied by L, right, and that should be multiplied by n because n number of capillaries are there. So, this is going to be total surface area of n number of capillaries of length L. Okay. So, now coming to the particle real packed bed. So, this is left hand side, it is about the capillaries which is equivalent to of our packed bed. We simplified it. Okay. So, now about the packed bed, 6 by pi s dP is what? It is the surface to volume ratio of the particles irrespective of the size and shape. It is true for all size, all shape, regular particles. Okay. This one multiplied by the volume of the particles. So, volume of the particles, how do you find? Let us say this is the packing here. So, these are packed between two perforated plates like this. So, the cross section area of this column whatever is there, that is S naught. Okay. Cross section area of the bed is S naught, and then height of the bed is L. So, volume of the bed is going to be S naught L, and then if you want to know the volume of the particles, out of this volume 1 minus epsilon volume fraction is occupied by the particles, remaining is the occupied by the liquid or void space. Okay. So, S naught L into 1 minus epsilon is going to be volume of all the particles that are present in the packed beds. So, surface to volume ratio 6 by pi s dP multiplied by S naught L 1 minus epsilon. If you do, you will get a kind of a true surface area of the packed bed. That packed bed, whatever the packed bed that we have taken, that is true surface area of the entire bed is this one, that is 6 by pi s dP multiplied by S naught L 1 minus epsilon. So, that should be equal to the total surface area of n number of capillaries, that is n pi d equivalent L. So, here S naught is the cross section area of the bed. Now, void volume in the bed is same as the total volume of n channels. Total there are n number of channels are there, whatever the volume of each channel is there, that if you multiplied by total n number, that should be equal to the existing void volume within the bed, because two are equivalent now. Okay. So, then when you do this one, so similarly as I mentioned that S naught is the cross section area of the bed, L is the height of the bed, the height of the packing that we have done. So, S naught multiplied by L is going to be volume of the bed, the entire volume of the bed, which is consisting of both solids and void space or the liquids. Okay. So, out of this total S naught L volume, only epsilon fraction is void volume. 1 minus epsilon fraction is solid volume. So, here we wanted to know the void volume in the bed. So, that S naught L multiplied by epsilon will give you the void volume in the bed. So, that void volume should be equal to the void volume provided by n number of or bunch of n number of capillaries or channels. So, their capillaries, we have this each capillary of size d equivalent diameter and then height same as the height of the bed. So, cross section of this capillary is pi d equivalent square by 4 multiplied by L. If you do, that is the volume of this capillary that is available for the flow. So, the fluid is flowing through. So, this volume of the capillary is now pi d equivalent square by 4 multiplied by L. This is volume of one single channel. So, there are n number of such channels, so that that whatever the total volume provided by this n number of channel is same as the void volume of the real packed bed. So, S naught L epsilon is equals to n pi d equivalent square by 4 multiplied by L. So, now what we do? We take 4 to the left hand side and then 1 d equivalent also we take to the left hand side. So, S naught L epsilon 4 by d equivalent. So, from here 4 we have taken left hand side and 1 d equivalent also we have taken left hand side. So, the remaining things are n pi d equivalent L. So, this n pi d equivalent L from just previous equation number 2, what we have we found it as 6 by pi s dp S naught L 1 minus epsilon. This is coming from equation number 2, right. So, now this part, if you equate to this part, right, then you can find it out an expression for d equivalent, right. So, that is what our target here. So, that we do now. This S naught you cancel out here, S naught cancel out, L and L also you can cancel out, 2 2s are 2, 3s are if you do it. So, d equivalent you take to the other side. So, here in the left hand side you have a 2 epsilon as it is, okay. And then from this side if you bring that pi s dp to the other side, so that will be multiplied and then 1 minus epsilon if you bring it to the other side, that will be divided. So, d equivalent what we get here by this simplification, we get it as 2 by 3 epsilon by 1 minus epsilon pi s dp. dp is volume equivalent diameter of the irregular particle that has been used for the packing of the column. Okay. D equivalent is the diameter of capillary, and there are n such number of capillaries are there which are forming a kind of bunch. So, that to have a same characteristics like packed bed in terms of the voidage epsilon and then surface area or surface area to the volume ratio. Okay. So, now here typical void fraction of 0.4 to 0.5 is in general possible in real applications. Let us say if you take 0.43 void fraction, then d equivalent you will get 0.503 pi s dp. Okay. So, let us say if it is a spherical particle, let us say the packing has been done with a spherical particle of diameter dp, then d equivalent is equals to 0.503 dp, because pi s is equals to 1 for spherical particle. So, what does it mean? If the packing is done using a spherical particle, then equivalent diameter of the which is required for the capillary, so that n number of such capillaries can form a kind of bed having a kind of equal characteristics as a kind of a true bed that we have taken, right. So, what does it mean? So, that equivalent diameter is half of the diameter of the sphere, right. If the voidage is 0.43 and the packing is done by the spherical particle, then equivalent diameter is half of the diameter of the spherical particle. Now, what we have to do? We have to find out the pressure drop calculations. So, delta P depends on the average velocity in the channels V bar, which is not known. Superficial velocity is known. how much empty tower velocity you are providing, that you can know, because average velocity is going to change from packing to the packing, or from packing is a kind of irregular packing, and then size and shape are different from shape of the particle is also irregular, and then size is also going to be different from one particle to other particle, then the channels are not going to be regular, right. Then definitely the velocity is not going to be, the average velocity is not going to be same from one experiment to the other experiments, that we cannot know. Okay. Or you can know from the experiments anyway by doing experimentally, but however in applications without this simplification theoretical analysis, why are we doing? Because without doing experiments a priori we can calculate how much pressure drop is required for a packed bed of certain height and certain porosity, etc. For that purpose we are doing it. Okay. So, then this V bar is proportional to superficial velocity or empty tower velocity V naught bar, and inversely proportional to the porosity. So, that V bar is equals to V naught bar by epsilon. So, in this equation in place of V, we replace V by V bar, that is V naught bar by epsilon, and then D we replaced by D equivalent, simply do that one. So, now the average velocity V bar and D equivalent will be expressed in terms of the measurable properties or parameters such as V bar, dP, epsilon, etc., and those things will be used in this equation. So, indeed D equivalent we have already represented in terms of this dP epsilon, and then VR just now we have seen it is V naught bar by epsilon. This information we are going to use in this Huygens-Poiseuille equation. Huygens-Poiseuille equation for laminar flow in straight tubes without any packing. In straight tubes without any packing, if the fluid is Newtonian and then fluid is flowing under laminar flow conditions, then pressure drop is 32 L V bar mu by D. This we already know here. So, then what we do here? We substitute V bar is equals to V naught bar by epsilon, D we replace by D equivalent and simplify. So, then when we do it, 30 delta P by L is equals to 32 V bar mu by D equivalent square. 32 V bar is nothing but V naught bar by epsilon mu, and then 1 by D equivalent is 2 by 3 1 epsilon by 1 minus epsilon pi s dP whole square, and this multiplied by a factor lambda 1. Why it is? Because in straight pipes, straight tubes, etc., like capillaries, if there is a laminar flow, when there is no obstacle, right. So, there is fluid elements are traveling the same distance as the height of the pipe or the length of that pipe that you have used. Okay. But in the packing, the fluid element, if you are packing that column with some kind of packing material, some particles, etc., then what happens, this fluid element is traveling more than the height of the packing because of the tortuous path. So, in order to bring in those information, we are taking this fraction lambda 1. Let us not worry about what is this lambda 1 value as of now. Now, this equation you rearrange and simplify it. So, then what we have, delta P by L is equals to 72 lambda V naught bar mu 1 minus epsilon whole square by pi s square dP square epsilon cube. This is what we are having it. Right. So, now here V bar is superficial velocity is known, how much velocity, superficial velocity you want to provide, that you know, and then viscosity of the fluid you know, the void space of a bed characteristics that in general you know, right. dP and the volume, sphere volume equivalent diameter of irregular particle you know, sphericity of the particle also you know, or you can know the way the calculation that we have done in module 1, right. So, then everything is known here except this one lambda 1, right. But this lambda 1 is a correction factor for tortuous path and non-straight non-parallel channels in general, irregular channel, that is what I already mentioned, right. But from experimental studies, empirical constant is found as 150 in place of 72 lambda 1. So, like you do the experiments, right, and then try to maintain the laminar flow conditions, then if you represent your results delta P by L as function of these parameters like this, you will get 150 V naught bar mu 1 minus epsilon whole square by pi a square dp square epsilon cube, or theoretically whatever the values that you get here, other than these things if you calculate, so that constant is coming out to be close to 150 value of experimental value, right. So, this delta P by L or the pressure drop, okay, pressure drop for a fluid flowing through packed bed of a packing height lambda, bed having the void space epsilon, then packing has been done with some kind of irregular particles. If the flow is laminar flow, then pressure drop you can calculate using this expression without doing any experimental studies, okay, because this has been found consistent with the experimental study if you replace that 72 lambda 1 as a kind of 150. Okay. This equation is known as the Koznik-Orman equation and valid for Re up to 1 only, small Reynolds number only it is valid. As I already mentioned, in the straight pipes without any packing kind of thing, we have seen that laminar flow conditions are existing up to Reynolds number of 2100 something like that, but if the same channel or the tube, if you have some kind of packing in between to have a kind of packed bed, so then the flow is not going to be laminar beyond Reynolds number of 1. However, some people take approximation of Reynolds number up to 5 to 10 is also laminar, but in reality this equation is valid only up to Reynolds number of 1. So, this is for the laminar flow condition. Same thing we do for a kind of turbulent conditions also, but before going to do this one, the constant 150 if you equate to the 72 lambda 1, then what you get, lambda 1 is approximately 2.1. It is fluid element is on average travelling twice the or 2.1 times the length of the packing or the height of the packing, which is a reasonable value for the tortuosity factor in general for tortuosity factor. So, that is not a kind of a very blind value kind of thing. So, that is acceptable one. So, equation A, it indicates that the flow is proportional to the pressure drop and inversely proportional to the fluid viscosity. So, this statement is also known as the Darcy law, which is often used to describe the flow of liquids through porous media. So, here we can see this V naught bar, the flow velocity, flow whatever is there, flow velocity is there, that is proportional to the pressure drop and then inversely proportional to the viscosity, which is consistent as a kind of a Darcy's law, which is used for a flow through porous media. And then other thing I was mentioning, like for a given packed system, if you calculate delta P by L experimentally, let us say if you use irregular small particles like cement, pigment particles etc., for which you do not you find very difficult to measure SP by VP ratio, you make a packed bed with those particles and then experimentally you find out what is this pressure drop, right. So, then from here you can back calculate what is pi s dp. So, that from here you can find out SP by Vp is equals to 6 by pi s dp. So, this is the other advantage of this equation. Only thing that for the particles for which you wanted to find out SP by Vp ratio, which is not possible or very difficult to find out using the other conventional ways because of inherent difficulties, then you use those irregular particles, small particles as a kind of packing material and form a packed bed and do the experiments, find out delta P or pressure drop experimentally. Okay. So, that pressure drop you can use here in this equation and then back calculate what is pi s dp, because remaining things are known. Experimentally how much superficial velocity you have given, that viscosity of the fluid and then void space of the bed in general or in general it is around 0.4 to 0.45. So, you can calculate pi s dp from here because rest everything is known. Once pi s dp is known, if you do 6 by pi s dp, you will get a surface to volume ratio for those particles. Okay. So, now making use of turbulent flow equation for flow in straight pipes for the present case. So, what we do, we have this friction factor expression F is equals to tau W by of rho V square for flow through pipes. So, this one we can write it as a kind of tau W we can write minus delta P by L R by 2, R is the size of the pipe of rho V square, you can do it. So, that means there is a relation between F and minus delta P by L. So, that relation, if you rewrite it here in this form, delta P by L is equals to 2 F rho V square D equivalent divided by D equivalent here. So, this R we can write it as D by 4 or D equivalent by 4. Then we have this equations, right, 2 1 ja, 2 4 ja, 2 1 ja, 2 2 ja 4. So, then we have 2 F is equals to minus delta P by L D equivalent divided by rho V square, or minus delta P by L is equals to 2 F rho V square by D equivalent, and then the tortuosity factor for a irregular packing that we are having in the bed, right. So, we are not writing lambda 1, we are writing lambda 2. Why? Because lambda 1 is valid for a kind of laminar flow conditions. So, if the flow velocity is changing, the fluid element that is traveling the tortuous path of that for a given fluid element may be different. Okay. So, let us take lambda 2. So, if you rearrange this equation like this, you have 2f lambda 2 rho. In place of V bar, we can write V bar V naught bar divided by epsilon, so whole square, and then in place of D equivalent, you can write 2 by 3 pi s dp epsilon by 1 minus epsilon. So, that you put it here, substitute here, and then simplify it. So, you will get delta P is equals to 3 f lambda 2 rho V naught square divided by pi s dp multiplied by 1 minus epsilon epsilon cube. Okay. So, lambda is a tortuous is a correction factor for the tortuosity or tortuous path that is existing in the packed bed. Now, an empirical correlation for pressure drop in packed beds at REP greater than 10 power 3 is known as the Burke-Plummer equation, and it is given as this thing. This is empirical correlation developed by Burke-Plummer. So, according to them, for the flow through packed beds, when Reynolds number is greater than 10 power 3, delta P by L is equals to 1.75 rho V naught square or rho V naught bar square divided by pi s dp multiplied by 1 minus epsilon divided by epsilon cube. Now, this equation number 10, if you compare with our equation number 9, just we derived theoretically, this is empirical correlation. Equation number 10 is empirical correlation developed by these people, Burke and Plummer. Okay. And then this is the theoretical equation that we just developed based on the theoretical information that is available. So, what we understand here, this 3f lambda 2 is equal to 1.75 and rest everything is same, right. So, although equations 9 and 10 have same form, the constant 1.75 is much higher than expected value based on friction factors pipe flow for the pipe flow cases, because for the pipe flow cases, so whatever the Reynolds number of 4000 is there in general for a packed bed, which is equivalent to Reynolds number of 10 power 4 in the case of pipe flow without any packing, right. Under such conditions, F is approximately 0.01 for smooth pipes. Okay. This is fanning friction factor versus REP for pipe flows. Charts are available. From those charts, we can find it out that at this Reynolds number, REP of 10 power 4 for pipe flow, at that Reynolds number, friction factor is approximately 0.01 for smooth pipe. In the pipe flow where there is no packing, if REP is order of 10 power 4, so that is equivalent to REP of 4000 in the case of packed bed in general. Okay. So, that is more than order of 10 power 3. So, if you use this one, this expression in place of 3f lambda 2 is equals to 1.75, you will get lambda 2 is equals to 58. So, so much high value which seems to be unrealistic in general, right, which is much too large to explain why the tortuosity of channels or roughness of particle surface is so large values like 58 something like this. However, we can use them with a constant 1.75 rather using 3f lambda 2. So, covering entire range of flow rates, one can obtain the pressure drop by assuming that the viscous losses and kinetic energy losses are additive, then we can have a kind of Ergin equation, or the first equation whatever that Kozny-Karman equation, that is delta P by L is equals to 150 by that expression. So, that is considering only viscous effect, small Reynolds number in the sense only considering the viscous effects, okay, it is not considering the kinetic energy losses. So, whereas the Burke-Plummer equation that we have minus delta P by L is equals to 1.75 and something, that expression, that is only valid for only large Reynolds number. If the Reynolds number is order of 10 power 3 or even more, that means only convection forces only dominates, inertial forces only dominates. So, that means they are due to the whatever the losses are there because of the kinetic energy losses are there. And then these two are the either extremes. One extreme end is the viscous losses or for the small Reynolds number cases, another extreme is for the large Reynolds numbers or for the kinetic losses, okay, or due to the kinetic losses. So, if you assume that these are kind of additive kind of thing for the intermediate range, then you will get pressure drop equation for the entire range of Reynolds number starting from small Reynolds number to the large Reynolds number. Okay. That equation when you add together is known as the Ergin equation, and then that we can write it as delta P by L is equals to 150 V naught bar mu by pi s square dp square multiplied by 1 minus epsilon square by epsilon cube plus 1.75 rho V naught bar square by pi s dp 1 minus epsilon by epsilon cube. Now, we can see the viscous losses are having some kind of 1 minus epsilon whole square by epsilon cube terms, and then the kinetic losses, the second term is having 1 minus epsilon by epsilon cube terms. Okay. So, one should be careful about them, and then indeed we can find out the reason why it is. So, this is the Ergin equation. This first part is Kozny-Karman equation, the second part is the Burke-Plummer equation. If you add them together, we get Ergin equation which is valued for all Reynolds number, small to large Reynolds number, including the intermediate range of Reynolds numbers. So, Ergin showed that above equation fitted for spheres, cylinders and crushed solids over a wide range of flow rates. He has done several experiments for different types of packing material by varying a large range of flow rates, and then you find that whatever the Ergin equation, that previous equation we have seen, that is valid for wide range of flow rates and then different types of packing material. He also varied the packing density for some materials to verify why 1 minus epsilon square by epsilon cube term for viscous losses part, that is first part in the right hand side, and then why 1 minus epsilon by epsilon cube part for the kinetic energy part, that is second part, that also he found. And then he found that small changes in epsilon has a very large effect on delta P, which makes it difficult to predict delta P accurately and to reproduce experimental values after a bed is repacked. Once the bed is repacked, what will happen? That is going to have a kind of void space is going to change. Okay, it is not going to be same packing as a kind of initial packing. So, under such conditions, once the repacking is done, so there would be small changes in epsilon, and then definitely the delta P is going to be strongly being affected by this epsilon. Okay. So, reproducibility of experimental results are found to be very difficult, especially when the bed is repacked. So, the references, the lecture presented here is primarily prepared from this reference book, Unit Operations of Chemical Engineering by McCabe, Smith and Harriott. The Unit Operations of Particulate Solids Theory and Practice, Ortega-Revas by Ortega-Revas can also be a good reference book. Carlson and Richardson's Chemical Engineering series by Richardson and Harker, second volume, is also a kind of good reference for this kind of this particularly flow through packed beds. Some applications have been taken from this reference book, Transport Processes and Unit Operations by John Copley for this lecture. And then some applications are also taken from this Carlson and Richardson's Chemical Engineering series, second volume. Other reference books could be like better options are Unit Operations by Brown et al. And then Introduction to Chemical Engineering by Badger and Banchero. Thank you.